applications of deep learning at DLHC.
All right, well, thank you very much to the organizers for the invitation. It was a real pleasure to have this opportunity to come back to Taiwan. My parents are originally from here, so they're still here now, so it's nice to come back. So I'm going to tell you a bit about some applications of deep learning at the LHC. It's based on this work that I did with my excellent postdocs at Rutgers, Marco Farina and Yuichiro Nakai, and my very good student, Sebastian Macaluzzo, who's on the job market this year. And since it's a rather diverse audience, I thought I would have a bit more introductory material at the beginning, since for some of you this may be the first time you encounter machine learning or its applications to the LHC. So just by way of some motivation, as you all know, the LHC has searched for new physics in many, many places. And so far, what we have to show for it are these unreadable limit plots showing the limits on new physics particle masses, reaching up to 1 and even 2, in some cases 2 TeV. And so far, there's been no evidence of anything beyond the standard model. And many, in particular, many well-motivated models like supersymmetry, quasi-Higgs, dark matter have not turned out as expected. And so I actually decided to quantify the level of interest people have in well-motivated models by scraping the archive for the number of FPH papers that have been written on supersymmetry and mentioning LHC in their abstracts as a function of time. And you can see that people are definitely losing interest in many well-motivated models. This is the fraction of papers, yeah. Yeah, you can plot the absolute value number. What's that? Oh, the absolute number of papers as a function of time is mostly constant. So people are writing roughly the same number of papers on different topics. Okay. So yeah, people are losing interest in these top-down ideas, and I think so we need new ideas to motivate new searches for new physics at the LHC. And in particular, I think we need to admit maybe we don't know what we're looking for. And so can we search for new physics in the data without knowing what we're looking for? How do we look for new physics in this extremely messy environment of a hadron collider and find something unexpected? And so a very extreme version of that is, can we find a needle in a haystack if we don't know what a needle is? So it sounds hopelessly difficult, but along comes this new breakthrough coming from the real world of deep learning and artificial intelligence. So there's some hope that when applied to the LHC, this could yield major new results. Okay, so recently there's been a lot of interest in applications of deep learning to the LHC. Here's a list of some of them. You saw a much fancier, nicer looking presentation from Spencer with pretty pictures. So this is just a review of that. So we've used deep learning at the LHC to do simple classification tasks, such as tagging different kinds of particles relative to other kinds of particles. People have used it to remove pileup in a much more effective way than just simple cuts. And people have even used it to start to replace event generators or detector simulations. And people are starting to use it for triggering and anomaly detection, looking for interesting or outlier events in the data. And so today, in this talk, I'm going to review some of the work that I've done in these directions, focusing on classification, tagging boosted top quarks, and anomaly detection. And so, in the work of many, many people, there have been very impressive successes, and especially very clear improvements for classification tasks, tagging, and these are beginning to be adopted by the LHC collaborations. Okay, so before I get on with the bulk of the talk, let me just set the stage by reviewing a benchmark application of machine learning and of something people are generally interested in at the LHC, and that's boosted resonance tagging. So the classic example of this is top tagging. So as you know, a top decays to a W and a B basically 100% of the time. And if it's a low momentum top, the W decays itself to 2 jets, and the 3 jets here are very well separated. But if the top is highly boosted, then these jets become collimated, and what you have are these 3 subjets inside a big, what's called a fat jet. And then it becomes an interesting question how to differentiate this fat jet that has a top inside of it from a regular QCD jet that's initiated from a massless gluon or a quark. So how do we tell the difference between these 2 types of jets? So the simplest thing to try is to look at well-motivated physics variables, such as the jet mass or some measure of the jet substructure, and just do simple cuts on these variables. So obviously, the jet mass for a top should peak around the top mass, whereas for QCD, it should be more or less a featureless continuum. So that's a nice variable to cut on. And also, the tops should have some lumpiness to them, approximating this 3 subjets inside this big fat jet, whereas the QCD jet should be relatively featureless, or more like a dipole. So this is a variable called n subjettiness that can discriminate between QCD jets and top jets on the basis of their substructure. Okay, so these variables have been studied extensively for many years, and this is a paper from CMS summarizing the state of the art that you can achieve when you do cuts, simple cuts on these kinematic variables. And this is, I think Spencer introduced this in his talk already. This is an example of what's called a rock curve, which will feature throughout the talk. It's a way of characterizing how well you're doing, and how well your classifier is doing. And so on the x-axis, you have the top tagging efficiency. So here's where you accept all the events as tops, and here's where you are very, very picky and reject all your events. It says none of them are tops. And versus here, this is the QCD jet mistag rate. So here, in this corner, you're accepting everything, and in this corner, you're rejecting everything. And so a better classifier lives more up here. Yeah. Okay. So, sorry, a better classifier lives more down here. Yeah. So this is an example of a rock curve that you get with cuts on kinematic quantities, and what I'll review in today's talk is that using deep learning instead of simple cuts, using deep learning you can do much, much better than these curves. So that's a real breakthrough that's happened in the last few years. Okay, so here's the plan of the talk. I'm going to give you a brief introduction to what deep learning is. There'll be some overlap with Spencer's talk, but maybe it won't hurt to hear it twice. And I'll focus especially on a type of deep learning architecture called convolutional neural networks that are used for image recognition. And then I'll show how these can be applied to jets at the LHC, where you think of the jet as an image, and show how that gives you a better top tagger. And finally, I'll get to the thing that we're really interested in, which is using deep learning for discovering new physics at the LHC. And there, the idea is again to take jet images and feed them into something called an autoencoder. Okay. So yeah, so what is deep learning? It basically refers to a powerful new class of neural networks with many, many hidden layers. And so what is a neural network? Well, a neural network is something that takes a series of numerical inputs and feeds them in this is called a feed-forward neural network. It feeds them to layer after layer, but always going in a particular direction until finally you get an output. And the output could be, say, a number between 0 and 1 that gives you the probability that your object is a top or a QCD jet. This would be a single output neuron, gives you a number between 0 and 1 that can be thought of as a probability. So this is an example of a fully connected or a dense neural network where the input is basically a vector, a column vector of real numbers. And then at every step, you have more real numbers that are basically functions of the layer before them. And the way that they're functions is you have a linear mapping, and then you have a nonlinear activation function. And this is supposed to be, I'm not an expert on neuroscience, but this is supposed to be somehow modeled on what the brain actually does. Okay, So, right, so the things in this neural network that are learnable are all the connections between layers that are represented by these weights, W. This weight here is a big matrix, and the biases here are column vectors. Okay, so all those things are trainable or learnable weights. So what these many hidden layers somehow enable the neural net to do is to learn more abstract concepts, such as this is a car, this is not a car. So more abstract concepts, starting from raw inputs, for instance, a picture of a car. And so one way to think about what these neural networks are doing is that they automate the process of feature engineering. And so this is a comparison between more conventional machine learning prior to, say, 2012, nowadays called shallow learning, and deep learning. So in shallow learning, you would take the input, which is a picture of a car, and then a person would figure out, oh, a car has 4 wheels, has windows and doors, and then you would input those numbers, those are called high-level features, to a classifier, which is still a neural network, and then you get an output, car or not car. With deep learning, you skip this step of the human coming up with counting wheels and whatnot, and you just feed the picture of the car to a neural network, and it figures out what the most important features are. It extracts the features, and then it gives you a classifier. And it turns out by automating this process, the neural network can learn extremely subtle correlations and subtle features that humans might not pick up on. But the flip side of it is it can also learn things that are not real, and that's called the problem of overtraining or overfitting. Okay, so the physics example that's relevant for this talk is, you have a jet, and you might come up with nice kinematic variables like the invariant mass or end subjettiness, and then you could feed that to a set of cuts and get a classifier out. You can also replace the cuts with a machine learning algorithm like a boosted decision tree. This is widely used by the LHC collaborations for many years now. And this gives you a better classifier, and this is an example of shallow machine learning. And then deep learning is basically replace everything with a black box. You just feed it the jet and let it figure things out. Okay. So being machine learning, the learning part is that neural networks need to be trained on a set of examples. So it's learning by example. And the goal of training is always to minimize something called the loss function that quantifies the performance of the neural net. And so the loss function is basically, if my output of the neural net is, in this case I'm trying to classify dogs and cat pictures, if the output is some probability that it's a cat, and I know the truth value, all my images are labeled, these are all dogs, these are all cats, so I know the true value, then I can train a classifier based on how close my probability is to the truth. Minimize this loss function. Could be a mean squared error, could be something more fancy called binary cross entropy. But anyway, it's some function which, if this L were 0, would mean you have a perfect classifier. And the smaller it is, the better you do it. Okay. So, of course, there's many stunning real-world successes in recent years, which I'm sure you've all heard about. There are apparently stores now where you don't have to pay or interact at all with a human. You just take something off the shelf and walk out the door, and it tracks you all the way through the store and charges your account automatically. They had the breakthrough with Go, and more recently chess. So now those are out of the realm of human competition, I guess. Also speech and text recognition, things like Google Home and Siri. These are all driven by the latest breakthroughs in machine learning for natural language processing. Okay, so in today's talk I'm going to focus on image recognition. And so, just a bit of history, in 1998, the first modern convolutional neural network was invented by these people, and it consisted of a number of layers called convolutional layers, and also something called pooling layers, and then finally some fully connected layers. And this was shown to achieve a breakthrough level of accuracy on a database of handwritten digits, so 99% accuracy on a database of handwritten digits, which then people like the Postal Service adopted to automatically read letters and things to know where to send them and all that, and also check handwritten checks and things. So this was a breakthrough in 1998, And they used a novel thing called a convolutional layer, which basically slides, so the input is a pixelated image, and so it has some two-dimensional structure to it. And so the idea of a convolutional layer is to exploit that two-dimensional structure by dragging a filter across the image. And this filter is a set of numbers which parameterize basically a feature. So for each feature that you want to learn, you need one of these filters. And by dialing these numbers in here, you sort of fit to different the features could be like circles and dots and lines and edges and different types of things that happen in the images. And so yeah, so the convolutional layer is the thing that learns two-dimensional features. So in 2012, the thing that really had a breakthrough, and this is when I think deep learning really took off, so it's just 6 years ago, a much more powerful CNN won a much more sophisticated image classification competition called ImageNet by a huge margin, and that's what I think a lot of people credit with launching the renaissance in machine learning. And so this was basically just a souped up version of this by a factor of 1,000. So they made it much deeper, gave it many more weights, trainable parameters, 60 million. And for the first time, it really required training on a GPU, graphical processing unit. And so putting all those sort of improvements together, they achieved something like, well, it doesn't sound that good, but it was a breakthrough. So a top 5 error rate of 15%. So it means that in the top 5 choices that it makes is the true answer, and it only makes mistakes 15% of the time. So that was considered a huge breakthrough because the next best was 25%. So this is what the ImageNet competition is. It's 1,000 different object categories with like 1 million images or so, and the computer has to look at this image and decide what the most important feature in the image is, and it gets basically five tries. Yeah, and you can see here it's doing mostly the right job, I guess. Anyway, so there are many improvements since then, and now the world best is around 2%, and that's claimed to be better than humans can do. Okay. And so just a bit about what the features that this thing is learning are. So the idea is that the deeper you go in the neural network, the higher the level of the feature it learns. So it starts off with low-level features in the earliest layers. These are just edges, basically, and colors and things. And then it starts to abstract more and more concepts until you're getting, wheels and faces and, real-life objects like doors. So it's learning, more and more abstract concepts as you go deeper. Okay. So that brings me to are there any questions about deep learning in general? No? Maybe you've all heard this before. Okay. So that brings me to the idea of jet images. So this really originated, I think, in this paper from 2014, the idea that you could think of a jet as an image and apply some neural network or machine learning to it. Maybe there were much older papers, but that's the one that, that's the last person to work on it, I guess. And so you can think of a jet in an obvious way as an image in eta and phi in the calorimeter. The calorimeter already has a pixelized aspect to it. It's already pixelated. So each pixel is a calorimeter tower, and then the intensity or color of that pixel is the intensity, how much energy was deposited there. And so for every jet, you get a nice looking image. The image could be rather sparse in general, but for every jet, you get an image. And then people realized that you should be able to apply off-the-shelf CNN technology to classify and analyze jets at LHC. So you notice there's a lag between physics and the real world. The breakthrough I mentioned happened in 2012, and the whole CS world was abuzz. And then physicists only caught onto it in 2015, 3 years later, which is like light years later in this community. So we're still playing catch up, I think. Okay, so the thing that Sebastian and I studied in our paper from earlier this year was how to do better top tagging with CNNs. So this is an example of a jet image from a top, or rather not an example, it's an average of many top jets so that it looks so nice and smooth, and an average of many QCD jets. With some specifications, we generated them with Pythia and Delphis, and they have a narrow PT range, making them fairly boosted. And there's about 1 million jets that we generated for each type, and then we pixelated the images and also gave it some colors, but here I'm just showing you the grayscale images. Anyway, you see that the tops have a clear substructure to them, whereas the QCD is more vertical looking. It's a dipole shower of QCD. And so we basically took the previous work on CNN top tagging by the Heidelberg group from 2017, and we improved it by a great deal. We really optimized it and showed for the first time that it could really outperform conventional methods. So this was the CNN that we developed. It has some 4 or so layers of convolutions, and then some fully connected layers, and then finally a simple softmax output. So you see that this is very similar to the CNNs that were developed for real-life image classification. Okay? And so this is how the classifier performs in terms of its raw output. So this is the neural network output. It's just a number between 0 and 1. And trained on tops and QCD, it produces this nice histogram where the tops are over here. Notice this is a log scale in the y-axis. So the tops are all clustered up here, and the QCD is all bunched up down here. And if you turn this into a ROC curve, so basically if you slide a cut across this histogram, turn it into a ROC curve, you get this nice looking ROC curve here. That's the performance of our CNN top tagger. And we showed that it was a factor of roughly 10 better than the one developed by the Heidelberg group, and a factor of 3 or so better than the state-of-the-art that you could do with cuts or high-level kinematic variables. So a factor of 3 is actually a very big gain in this field. People are interested in usually in 10%, 20% improvement. So for deep learning to come in and do factor of 3 better is pretty striking. Okay. So yeah, so let's see. So top tagging is a prime example of top tagging is a prime example of what's called supervised machine learning. That's training with data sets where you already know all the truth values, so every example is fully labeled. And supervised learning is great if you know what you're looking for. But we're interested in searching for the unexpected, so that's my real interest here. And so, if the data has a small signal in it and we don't know what that is, how do we train a neural net to find it? And so that's a much harder problem. And so that falls into classes we call unsupervised learning, or training on unlabeled data sets. Okay. So here's a table just comparing the 2 types of machine learning, supervised or unsupervised. In supervised learning, you're training on labeled data. Unsupervised, you're training on unlabeled data. So each example comes to you and you don't know what it is ahead of time. So for supervised learning, you need to train on a separate data set, either data that's been labeled, real-life data that's been labeled, or simulations where you know everything ahead of time. Whereas for unsupervised learning, since you don't know anything anyway, you can train directly on the entire data set. You can just train directly on the data. And supervised learning is useful for prediction, for predicting whether something is, so basic classification. And unsupervised learning is useful for actual analysis. And so for supervised learning, you can apply it to classification and regression, whereas unsupervised, it's more for applications like clustering things into signal and background, or anomalies and boring, or normals. Okay. So the idea that we had for how to do unsupervised machine learning for anomaly detection at the LHC is to apply something called an autoencoder to the data. And so we put out this paper in August, and simultaneously the Heidelberg group also, we coordinated the publication. We basically have the same idea. And so this autoencoder is a well-known tool, I guess, in the real world. And it's a way of learning an optimal compression. So it's a way of learning the hidden representation of your data set, the hidden knobs that control the variations of the data set. Okay, so it consists of something called an encoder, and it consists of plus something called a decoder. So you can think of the encoder as just a compression algorithm. it takes the input and compresses it to something which is much smaller. So think of MP3 or something. The novelty here, though, is that it doesn't. You don't give it the compression algorithm ahead of time, but rather it learns that. So the compression encoder layers map it to some hidden representation called the latent layer, and then you have a decoder which maps it back to the original representation. Okay, and so the reason this is not trivial is that there is some information loss that happens from here to here. So going from here to the latent layer, you throw away some information. It's not a perfect compression, but it's a lossy compression. And so you can basically train the autoencoder to learn the most efficient representation of your data. And so the metric you want to use is basically how similar are the inputs and the outputs. How well did I learn the identity mapping? Without being able to actually learn the identity mapping. Okay. So the idea that people have had already in the real world is that you could use something like an autoencoder to look for anomalies, to do anomaly detection. And people have applied this to, say, fraud detection, credit card fraud detection, other anomalous behaviors, things in videos or self-driving car where there's something in the middle of the road that's not supposed to be there. So this is being applied to things like that. And so the idea is that if you train it train the autoencoder on a set of only normal events, so it learns to reconstruct those well. Those have a small reconstruction. The metric should be something like a reconstruction error. So the difference between the input and the output, say the mean squared difference between the input and the output. Okay. So you can quantify the performance of the autoencoder using this reconstruction error, and then you can train it on a set of normal events. These are the events that you're not interested in. They're the boring ones, everyday things. And so seeing those over and over again, it learns to reconstruct them well. And as a distribution, it has a small reconstruction error with some kind of tail. Okay. Then when it comes to see something anomalous, so basically with the normal ones, it learns to reconstruct them well by learning how to compress them efficiently to this latent layer. Okay. Then when it sees something it hasn't seen before, something anomalous, its performance should be worse, as in it doesn't know how to compress this weirdo example. It doesn't know what to do with that. So it tries the best it can, and it gets a much worse reconstruction of that. And so by cutting on this reconstruction error, you can remove, if this works, you can remove all the normal events, and you're left with just the anomalies. And you can do this in a way where you can do this in principle directly on the data, or just on simulating the background. Okay, if you do it just on simulating the background, this is called one-class classification, or it's an example of weakly supervised learning. If you do it directly on the data, it's an example of unsupervised learning. Okay, so this was the autoencoder that, we actually studied 3 autoencoders, but in the interest of time, this is the main one that we studied. It's a CNN autoencoder, where it's just a CNN, basically it's the CNN that we had studied before for TOPS, but then reflected onto the other side. So instead of doing this, what's called pooling here, you undo the pooling by upsampling. And so you get an output that's necessarily fuzzier than the input you put in, but still you can think about this reconstruction error. It's still useful. Okay, so we took the same jets that we studied for top tagging. We took the QCD jets as background, and for signal we considered things we were trying to discover. We took boosted tops and also 400 GeV gluinos decaying through RPV, just 2 benchmark examples. And we took those as signals. We made images out of them exactly as in the previous work, and then we trained our autoencoder on it. This is the result we got. This is the input. These are average images. So this is the input for QCD backgrounds, tops and gluino signals, and this is the output of the autoencoder. And you could sort of maybe see by eye, but maybe not from where you're sitting, that this is pretty good, and these are worse. If you look at the difference between this and this, that's shown here, where the darker colors are the ones that differ more, you can see that the tops and gluinos really are more different than the QCD. So just by eye, you can see in these images that the algorithm, the autoencoder algorithm works when it's trained on just the QCD backgrounds. This is more quantitatively a histogram of the reconstruction error for QCD. This is a log scale here, going down to 10 to the minus 7. So QCD is this gray thing here, and the signals are peaked here. So you can see that, yeah, it's really working as advertised. The signals have a much worse reconstruction error compared to the QCD. Okay, if we just imagine cutting here, we could remove a lot of the QCD background and be left with just the signal. And the important thing is here we didn't tell it what signal to look for. We just trained it on the backgrounds only. So in principle, this could discover many signals and unexpected ones. Okay, so that's if you train it directly on the background. Now what about if you train it on the data? So suppose the data has a little bit of signal in it. Okay, does that screw up the training of the autoencoder? So we studied this by taking a sample of QCD background, and we contaminated it with a small fraction of signal, going all the way up to 10% signal. So this could be representative of actual data. Maybe your data is mostly QCD, but buried in it is a small signal. And we trained the autoencoder on it, and we asked if we cut on the auto reconstruction error such that we remove 90% of the background, or 100%, or 99% of the background. So keep just 1% of the background. How much signal do we keep? What's the signal efficiency? So that's a plot of that as a function of the contamination ratio. And you can see that as I add more signal in, it does get worse, but not a whole lot worse. So the CNN autoencoder that I've been talking about, that's the one in red here, you can see it goes from 70% signal keeping down to 60%. So that's actually not bad, even with 10% signal in there. So basically what the autoencoder is learning is it's learning to ignore the 10% of the signal that's in there and just get the background right and minimize the total reconstruction error in such a way. Okay, so this is very encouraging. It means that we might be able to actually just train the autoencoder on actual data and then see if any anomalies emerge. Okay, but then you realize, well, how would you actually discover new physics with an autoencoder? You can't claim a discovery unless you know what your background is, right? So you can't say you can't just cut on the autoencoder reconstruction error and say all those events are new physics. There's still some standard model background, right? There's still some tail to the QCD background. So you need some way of estimating the background, and you want it to be data-driven, so you can't, in general, you can't rely on simulations. They're not accurate enough, plus all this deep learning stuff is a black box, so you really don't know what's going on. So simply counting the number of events above the threshold in reconstruction error is not enough. So say I just have say this was the actual data, and I train my autoencoder on the data, and I cut on the reconstruction error. Okay, well, what does that get me? That gets me some number of events above this threshold, but how do I know how many of those events are standard model and how many of those events are physics? I need some prediction for the background, otherwise I don't know if I have an excess or not. Okay, so, and using this data, using this unsupervised learning, I'm not allowed to look at simulations, right? Okay, so one idea we had is to combine the autoencoder with a bump hunt in JetMass. So okay, now I'm putting in a little more information. I'm saying, suppose my new physics signal is peaked at some mass. I just don't know what that mass is. Maybe it has some other characteristics to it, like jet substructure. So if it's a bump hunt in JetMass, I can estimate my backgrounds using a sideband method in the JetMass distribution. But this only works if the JetMass is uncorrelated with the autoencoder loss. Basically, if I cut on the autoencoder reconstruction error, I shouldn't sculpt a peak, a fake peak in my JetMass distribution of the background. Okay, so this is a somewhat technical point, but it's actually important. Otherwise, you can't use this. And so what we showed is that cutting harder and harder on the reconstruction error, the JetMass distribution is stable. So you don't get some, as you cut harder and harder on the reconstruction error, you don't get some fake bump emerging from the JetMass distribution. It's a smoothly falling thing, at least above a certain value. Okay. So you can use this to look for a bump in the following way. This is before any cut on an autoencoder. This is the actual 400 GeV gluino sitting there, normalized to its leading order cross-section, and this is the actual QCD dijet background. So you see that this bump may be hard to tease out of this background. If we now cut on the autoencoder to remove, I forget what we removed here, something like a factor of 1,000, a rejection factor, so keep just 0.1% of the background, then you see that it throws away most of the background, but it keeps a good chunk of the signal, and this the bump relative to the background is greatly enhanced. Okay, and there's no real artificial peak in the QCD jet mass distribution. So this is just to show that you could train directly on data that contains some gluino, some signal in it, and you can use the autoencoder to clean away the boring QCD events, enhancing the bump hunt by a lot. So in principle, you can actually discover new physics this way. So there are experimentalists right now who are they can't tell us what they're doing, but they're applying this to their actual data. They just make an M2 pool with jets, supply this very simple thing to it, and look what they find. There's some question of how you would phrase a null result. If you don't find something, what does it mean? How do you write a paper on that? But let's not worry about that until we don't find something. That's what I would say. Okay, so anyway, so that brings me to the end. Hopefully you walk out of here understanding that deep learning has revolutionized the field of artificial intelligence and has many stunning real-world applications, and that this revolution is more and more rapidly accelerating coming to high-energy physics. In this talk, we gave an overview of deep learning and computer vision, and we described two of its applications that I worked on to high-energy physics. It's top tagging and autoencoders. This is supervised learning, this is unsupervised learning. And just as a final point, you could ask how well does the unsupervised learning do relative to the top tagger I talked about here. This is much, much worse. So, and that's not a negative thing. So you can't expect unsupervised learning to give you better performance than supervised learning. Things are always better when you know what you're looking for. But the promise of something like the autoencoder is that it gives us the hope of discovering something new and something surprising. And I think we all need more ideas like that for how to look for the unexpected. Okay, thanks.
Technical question. So when doing top versus QCD, just supervised learning, so I think ROC 98 something, 0.98 something is super high, I think. So I think, what's the top PT you're using?
Yeah, so the specifications are here. I went rather quickly over this part. The PT range is 8.
So it's a really high PT. So so what's the performance for lower PTs?
So yeah, we studied that. I don't know if I don't think I have a backup plot, but it's in our paper. These numbers were taken from the CMS paper that studied top tagging and cut-based approaches to top tagging. So they have.
So it's a fair comparison.
Yeah, we tried to make it apples to apples as much as we could, and we also studied 350 to 450 PT range in our paper. Yeah, so it gets better with higher PT.
Yeah, so that's the concern.
Yeah, I think the comparison here is not the overall number, but the relative comparison.
Yeah, so yeah, but in real life, like when you have an actual signal and you want to like take something from that, that's absolute value is important.
Yeah, but I think the details are so important that I wouldn't read too much into the absolute value because, like you say, changing the PT range, it just changes everything by a lot. Yeah. So yeah, here it's just the relative.
So David, can you comment a little bit about, so here in images, many of the things that you're trying to reconstruct have the same kind of units. What would you do to, like, if you had just like a simple set of particles and they have different angles and you have momentum? What do you do something to standardize the variables for the autoencoding?
Yeah. So is it for the autoencoder in general for jet images? Yeah, we standardize the images so that all the pixels, the different colors that we use are numbers between 0 and 1. So we normalize the whole thing to unit PT. We also rotate them and flip them and things like that. But yeah, basically, if any, as you know, if any of the inputs are bigger than 1 or much bigger than 1, that screws up the training of the CNN. So yeah, in some sense, we remove the units by normalizing them. Yeah. Does that answer your question?
I guess in terms of the autoencoding, I'm concerned about when something reconstructs poorly, right? That there may be differences in terms of, say, a PT versus an angle, or things. Some might be more poorly measured, right? So, a more realistic method, you have to think about whether you need to kind of take those into account, right? In terms of reconstruction error.
Yeah, I guess you're saying maybe you want to normalize the reconstruction error to some actual resolution on these individual things. Yeah, that's not something we consider, but since we're just lazy theorists, but yeah, that sounds like something. We wouldn't be able to model those resolutions very well, especially the non-Gaussian parts of them. So that's probably something an experimentalist would want to worry about. Yeah, thanks.
So in more traditional forms of statistical analysis, you have problems with look elsewhere or variance of that. Just if you do many tests, you might come find some where there's an anomaly that's significant. So am I right that this sort of makes this much worse? Because you're kind of asking this black box oracle to look for anomalies.
I actually think this makes it much better. So rather than having many buns or many distributions, here it compresses it all to one distribution. So that is something we didn't sell very hard in our paper. But I think people, like your colleague Kyle at NYU, they care a lot about the look elsewhere effect, and for them, this is a selling point, I think. That here there's just one distribution. So the look elsewhere, first of all, it's very easy to quantify the look elsewhere effect, as it is in any bump hunt. But also, it's not, you're not multiplying those elsewhere effect by having a highly multivariate distribution.
But you don't know what the space is that the algorithm looked at. Right? I mean, because with the bump hunt, it's pretty easy to quantify. But more generally, if you just look for anomalies in data, there's so many different tests you could have done that it's pretty much impossible to quantify, how bad the look elsewhere effect is.
But I think this is giving you a somewhat quantitative or rigorous way to quantify that by mapping it all to this one space, basically. So just looking for a tail on that or combining with bump hunt, it's pretty rigorous, I think.
And then if you want to see if it holds up, you collect more data, and then if you
move these to lunch, you have to move on. Yeah. But maybe some very quick comment or question from this side. Good. Okay. If not, let's thank David again.